class. Okay, we're going into an entirely new topic, section 3 out of 4, so we're halfway done with the class. And we're going to talk about, I'll just label this, we're going to talk about magnetic forces. Okay, so, I'm sure everyone's seen magnets before. You know they can exert forces on certain metals, like nickel or iron, steel, things like that. And we want to talk about magnetic forces. Now, we talked about electric charges, where say we have Q1, Q2, and we can talk about the force between these two charges. Just Coulomb's law, we can just write it down directly. And do we think, like, what is the source? Like, why are there forces here? It's due to these charged particles that exert force on each other. That's what charges do. So we have, like, a source, like, where this force is originating from. And then we can talk about the effect, which is the force between these two charges. Now, it's a little difficult to do with magnetic fields. We're going to actually do things a little backwards when it comes to magnetic fields. Because, like, what is the source of a magnetic field? You might think, well, magnets. But, we have to talk about what magnets actually are. But ultimately, the source of a magnetic field is a current. But we're going to take kind of a backward. So we could talk about, like, say we have two wires carrying current. What forces do they exert on each other? Something kind of akin to Coulomb's law. We're going to take a different approach. So just like when it came to electrical charges, we came up with this idea of an electric field and then saw the effect of that electric field. And we're going to kind of do the same thing with magnetic fields. But we're going to start out by talking about magnetic, we're going to assume the existence of magnetic fields. So we'll say, we'll just assume that a magnetic field exists, talk about what effect that is going to have, and then after that, we're going to talk about where that field came from in the first place. So for now, we're just going to assume that a magnetic field exists. Magnetic fields are vectors, and we use the letter B to represent magnetic field. Now, M is used in a lot of things, so we use B to represent magnetic field. Okay, now what do magnetic fields do is they exert forces on moving charges. Or they can exert forces on moving charges, not always, but generally they do. So let's say we have a charged particle moving with a velocity v in a region with a magnetic field. So the velocity and the magnetic field both have directions. So we can represent both of these with vectors, and there's an angle between them. Now I should point out there's kind of two angles between them. One is this angle, another would be this angle, but that one, there's always going to be one, less than 180. Like between 0 and 180. Now if these were exactly opposite, then it would equal 180, but that's a special case. So generally we pick the smaller of the two angles. That's how we define theta. So again, we're assuming the existence of a magnetic field. We have a charged particle, and I'm just right now claiming that this charged particle is going to experience a magnetic force by moving in this magnetic field. So when we talk about magnetic forces, there's two things. We have the magnitude of the force and the direction of it. And we're going to start out by talking about the magnitude of the force. So here we have a charge Q. And I'm just going to write down the equation. I'll write it down over here. So force is QVB sine of theta. So charge, velocity, magnetic field times the sine of the angle. Okay, now let's talk about units. Now the basic SI unit for a magnetic field is something called a Tesla. So we have Tesla. Well, the unit would be lowercase, named after Nikola Tesla. So his name is capitalized, but units are not supposed to be. So Tesla is the unit of a magnetic field. And it turns out a Tesla is a pretty large magnetic field. Normally we'd use like milliteslas or even microteslas to measure the strength of a magnetic field. Getting in the Tesla range, the only thing I can think, or like an obvious example of something that would have a very large magnetic field, would be like an MRI machine. They have extremely strong magnetic fields. Those are usually around 1 to 3 Teslas, depending. Like the stronger the field, the better resolution they get. But that can actually cause a little problem. That can cause some problems health-wise if you go too high. And magnetic fields that strong are actually dangerous. There was actually a story where someone brought one of those oxygen containers into a room with an operating MRI, and he got pulled. It pulled him into the machine and pinned him there, and they could not remove him until they turned off the machine to get rid of the magnetic field. So yeah, they're extremely strong fields. That's just like 1 or 2 Teslas, maybe 3. I think the biggest field we've ever made in a laboratory was like 40 or something Teslas. That would be extremely strong. The Earth typically has a value of around like 0.5 milliteslas, or no, I think it's even, yeah, I'd have to check on that. It's, yeah, somewhere around like in the millitesla range, even smaller than that. So, yeah, typically the magnetic fields we work with are going to be smaller than that. But that's the basic SI unit. And we get a unit conversion factor here. So force is in newtons. Charge is in coulombs. Velocity is meters per second, but I'm going to multiply both sides by a second. And then we have a magnetic field in Teslas. So here's another one of these unit conversion factors. A newton times a second is a coulomb times a meter times a Tesla. Okay, so we've got the magnitude of the force taken care of. We have an equation there, you just plug things in. So that's the easy part. But then comes the direction part for magnetic fields, and this is where things get kind of interesting. So to start out with, let's just make an observation here. If theta is 0, let's draw that picture. So we've got a magnetic field in this direction and some charged particle moving in the same direction. That would be theta equals 0. To draw the theta equals 180. So this is called like velocity and the magnetic field are parallel. When it's a 180-degree angle, they're pointing in opposite directions. So it's parallel lines, but because they have directions, this is called anti-parallel. But we can see in both of these cases, the force is going to be 0. So sine of 0 is 0, sine of 180 is 0. So as far as the direction of the force in these two cases, we don't have to worry about that. There is no force, so it doesn't have a direction. So let's assume that the angle is anything other than 0 or 180. And then these vectors are pointing in different directions, and so they define a plane. Like if we had, say, V and B were parallel to each other, they wouldn't uniquely define a plane. Like, they both exist in the board. They exist in this plane. We could draw a board, perpendicular to this one, and they exist just as well in that one, or you could rotate it at some angle. But as long as there's no unique plane that these two pass through. But again, we don't have to worry about those cases because the force is 0 anyways. So anytime we want to know the direction of the force, these two vectors define a plane. And so we have a unique plane here, and the force is going to be perpendicular to that plane. So the force, I'm going to write this down. Force is perpendicular to the plane defined by V and B. So, let's say this board is our typical XY coordinate system. Then Z is coming out of the board, or going into the board. So we do Z as our third dimension. So basically the force on this charge would be in the Z direction, or the negative Z direction. We have to determine which. But it's perpendicular to velocity and the magnetic field. Now, to find the actual direction of the force, we use something called the right-hand rule. And so there's different variations of it. I like this kind of active version of it, where what you do is you place your fingers in the direction of the velocity. So you can do it this way, or this way, or this. There's a lot of ways you could orient your hand so that your fingers are pointing in the direction of the velocity. But you want to do that in a way that you can curl your fingers towards B. So like here, V is in this direction, I curl my fingers towards the magnetic field, and my thumb is pointing out of the board. And so according to the right-hand rule, that gives you a direction. Let me look at a different example. So here, I'll just say out of the board. Okay, so again, V, curl your fingers into B, that's out of the board. Let's say we have V and B like this. Now, pretty big angle between them, but again, you want to go the shortest way from V to B. So here, you have to orient your fingers this way and curl into the B, and thumb points into the board. So here the right-hand rule would point into the board. And obviously, as the name suggests, you have to use your right hand to do this. I have seen on exams, you see students writing with their right hand, and because that's occupied, they use their left hand, and that's probably not a good sign. Your left hand will just give you the opposite answer, so you can just flip it over. But it's called the right-hand rule, so stick to using your right hand for it. Typically. Okay. So it gives you a direction. Now, what is that direction? Like, what does that mean? I'll write it here. Right-hand rule. I'll just say RHR for right-hand rule. That gives you a direction, and the magnetic force. Yeah, maybe I should write it that way. The force is in the direction indicated. I'm just going to say direction. Even though grammatically I don't think that makes any sense, but force is in the direction of the right-hand rule. Should be like the direction indicated by the right-hand rule, and then have room to write that. But I think you know what I mean here. If the charge is positive, so like, let's say this is a positive charge moving in this direction, Again, the right-hand rule gives you a direction out of the board, and if this is a positive charge, then the force would be out of the board. If it was a negative charge, then it's the exact opposite. So opposite direction for a negative charge. Okay, so yeah, like if this is a positive charge, the force would be out. If it was a negative charge, the force would be into the board. Here, if this was a positive charge, the force would be into the board. So again, that's a very easy mistake to make, to just do the right-hand rule and say that's the direction of the force. You'll get that right half the time, but if it's a negative charge, you have to remember to reverse that direction. So in theory, we covered this topic, magnetic forces. Forces have a magnitude and a direction, and we've got both. Magnitude is given by this. The direction is given by the right-hand rule and the sign of the charge, positive or negative. So in theory, we're done. But again, the right-hand rule is one of those things, it's not at all complicated, but it takes some getting used to. It just seems kind of strange. But magnetic forces actually are kind of strange. Maybe I'll talk more about that later. But let's move on. Now, one thing that's interesting, or maybe that's not the right word, maybe kind of complicates things. When dealing with magnetic forces, we're kind of forced to deal with 3 dimensions. And we like to draw out problems on the board so we can visualize them better. And so that's a bit of an issue. So like basically we have force, velocity, and magnetic field. These are all vectors. And they cannot all point in the same plane. They can't all exist in the same plane. Like the magnetic force is always perpendicular to the velocity and to the magnetic field. So again, we're forced to deal with 3 dimensions. So when it comes to drawing things, like drawing problems, we usually pick the magnetic field to be in the, perpendicular to the plane. So a magnetic field is usually the one that we pick to be like either coming out of the board or going into the board. And so to represent this graphically, we have this convention. We have into the board, or out of the board. So into the board, if we want to represent a magnetic field going into the board, we can draw X's. And out of the board, we draw dots. Now it's kind of a funny way to keep these straight in your mind. Think of arrows. Picture an arrow fired out of like a bow. So like if the arrow is coming out of the board, it's coming towards you, you see the arrowhead. If the arrow is going into the board, you see like the feathers at the end that form these X's. So it's a good way to keep it. This is a convention that's, again, kind of just made up, but everyone agrees on this as far as I'm aware. Something we need to know. Yeah, it's very often used. Okay, so, and then we could draw let's do an example. Let's say we have a positive charge that's going to enter this region with a magnetic field. So what's going to happen when it reaches this magnet? Like say it just enters this region with a magnetic field. Well, we know its velocity is upwards. And remember the right-hand rule? Use the velocity in the magnetic field. The magnetic field is into the board. So what you do is you have to put your fingers this way, so you can curl them into the board, and then your thumb points to the left. So the magnetic force would be to the left. And again, the right hand rule gives us this direction to the left. We also want to check this was a positive charge. So that, then the force would just be in the direction given by the right hand rule. Okay, let's do another example. Let's say we have an electron, or any negative charge really, moving into this magnetic field. What direction is the force going to be? So here, let's do this. Velocity in this direction. Magnetic field's coming out of the board, so we'd have to orient our hand this way so we can curl out of the board. Right hand rule gives us the upward direction. However, it's a negative charge, so the force on this particle would be downwards. So you never want to forget that last step. Should point out, some people use this convention, and it's totally fine. You can use your right hand for positive charges and your left hand for negative charges. Like if you use your left hand, you'd have to put your fingers this way, curl out of the board, thumb points down. So you can think of it that way if you like. Use your right hand for positive charges, left hand for negative. But most people just use your right hand and flip it over if it's a negative charge. Okay. I think we have one more topic to talk about. Oh no, a couple more. So let's say we have a current. So like we have a wire carrying a current. Say we have a wire with a length L carrying a current I. And say there's a magnetic field B. And so again, the current is moving charges. Magnetic fields exert forces on moving charges. So there's going to be a force on this wire. We want to know what that force is. And what we're going to do is a massive simplification, but it gives us the right answer. Because remember, what's actually going on in a current is very complicated. These electrons are moving around in a somewhat random way, but there's a force pushing them to the left. But some of the electrons are moving right, some are moving left. It's just there's a little bit more leftward motion. But they're really moving in 3 dimensions. And so it's a fairly complicated motion we're talking about. But we can visualize our current as just positive charges moving in the direction of the current. Just moving at a nice constant velocity in the direction of the current. And so let's calculate the force on this charge here. That would be QVB sine of theta. Now, let's say this charge is moving with a velocity v. And again, we're assuming that all these charges are moving at the same speed, just nicely along this wire. Not very realistic. But if they're moving at a constant speed, we can say that L equals V times T. Like, it'll take a certain time for this charged particle to move from one end of the wire to the other. And so, let's plug that in. So we have, and let's say in a time t, a total amount of charge, let's call it delta t. Now let's call this delta q. So what we're saying is in time delta t, a total amount of charge delta q is going to move from one end of the wire to the other end. And so, the force then would be the total charge times v sine of theta. And if the time is delta t, the length of the wire is v delta t. So let's plug that in. We have delta q times v, which is L over delta t, times b sine theta. And now what I want to do is just rewrite that a little bit. Let's just move the delta T over. Remember, our definition of current is delta Q over delta T. So we have a force on a wire. This has to be a straight wire. If the wire was curved, then the angle between the velocity and the magnetic field would be different for different parts of the wire. So we're not going to worry about those. So the force on a straight wire due to an external magnetic field is ILB sine of theta, where theta is the angle between the current and the magnetic field. So in a sense, it's nothing really new. We just took the force on a charge and applied that to a current. But in a current, we really don't know the velocity of the moving particles and things like that. So this is a useful enough equation. This made it into the equation sheet. F is ILB sine of theta, where theta is the angle between the current and the magnetic field. Okay, that's something that's going to be useful later on. Okay, now I want to talk about work done by magnetic fields. Now, let's look at an example. Say we have a charged particle that's moving to the right. In a region with a magnetic field, let's say into the board. Okay, so there is a force on this charge, and again, more practice. Right-hand rule, velocity, fingers in direction of velocity, curl into the board for the magnetic, into the magnetic field. And so magnetic force is in this direction. Now, it's moving in the direction of the velocity, and what we notice is that the velocity and the force are perpendicular to each other. So in the case of like a constant force, the work done by a force is the force times the distance times the cosine of the angle between them. And for magnetic forces, the angle, it's always perpendicular to the direction that it's moving. So this angle is always 90 degrees. And cosine of 90 degrees is 0. So what we've concluded is that the work done by a magnetic field is always 0. It's kind of an interesting result. You can picture like a magnet picking up paper clips or something. There's work being done on that paper clip. It's being, there's a force lifting it up. It's an upward force, it's moving upwards. So there is definitely work being done on that paper clip. However, it's not the actual magnetic field itself that's doing the work. So, we'll talk a little bit about like the interaction of like magnetic fields and matter. It's kind of a complicated thing. But yeah, so the magnetic field itself does not do any work. So there's two things. We looked at an example. Let me draw a picture again. So yeah, let's say we have a magnetic field into the board. Say we have a charged particle. We fire it, so it's going to move and it's going to enter this region with a magnetic field. And once it enters, we can say its velocity is in this direction. Again, velocity, curl into the board. It's a positive charge, so the force is going to be in the direction given by the right-hand rule. So here we have our velocity and our force are perpendicular to each other. Now, if this field is strong, that's going to cause the, it'll affect the motion of this charged particle in a noticeable way. And so this charged particle, if we look at a different point, if the particle's over here, its velocity might be in that direction now. But again, V, curl your fingers in the direction of B. The velocity and the force are always perpendicular to each other. So there's two things we need to note here. Velocity and force are always perpendicular. And the magnetic fields, or magnetic forces, do no work. Okay, now this might seem familiar, you might have seen this before, but what we have here, these two facts combined give us circular motion. I should say uniform circular motion. If we put these two together, like if you picture a mass on a string moving in a circle, like this end is fixed and the string is moving in a circle, like the force is always perpendicular to the direction that it's moving, and it's just moving at a constant speed. Oh yeah, so I mentioned that magnetic forces do no work. Remember the work energy theorem, where the net work done on an object is equal to the change in kinetic energy. Say there's no other forces involved. If only the magnetic force is acting, well, the net work would be 0. That means no change in kinetic energy, which means we're moving at a constant speed. So our constant speed and the force always perpendicular to the direction it's going. You put those together and you have uniform circular motion. So I'm going to erase this and going all the way back to 121, remember the acceleration, or at least the magnitude of the acceleration for uniform circular motion is v squared over r. And the direction is inwards towards the center of the circle. Okay, so this is a very common occurrence with charged particles moving in magnetic fields. We get this uniform circular motion. Now, let me look at an example of this. Actually, what I'm going to do, there's kind of two more things we should talk about here, actually. But I'm going to talk about one, and then maybe I'll do a second one on a second video, we'll see. But let's say we have a positively charged particle moving to the right with a particular velocity. And let's say we have, it's going to enter a region with a magnetic field that is into the board. Okay. So what happens when we enter this region? Remember, fingers in direction of velocity, curl in the direction of magnetic field. So here's our positively charged particle. I'm going to call this FB for magnetic force. There's going to be an upwards magnetic force. Now, let's say that we have a downward facing electric field in that same region. So the magnetic field is into the page, the electric field is downward. Now, the electric force on an object, I'll write that down as well. That's a much simpler one. That's just Q times E. And in magnitude, the direction of the electric force on an object, if we have a positive charge, the electric force is going to be in the same direction as the electric field. And we have a positive charge, so the electric force is going to be downwards. So we have a magnetic force upwards and electric force downwards. Now let's look at the magnitude. Let's say this is our positive y direction. The net force in the y direction we'd have the magnetic force, which is QVB. I didn't write sine of theta because the velocity and the magnetic field are perpendicular to each other. So the angle is 90 degrees. Sine of 90 is 1. So the upward force is QVB. The downward force is QE. Now we can factor the Q out if we like. So that would be the net force in the y direction. Now what's interesting here is that this force depends on the velocity. So say you have a particle going very fast. VB is going to be large, it's going to be bigger than E. So again, the faster it's moving, the stronger the magnetic force is going to be. So if you have a particle moving very fast, it's going to curve upwards like this. Alternatively, if we have a particle that's moving very slow, there's not going to be much of a magnetic force. The electric force doesn't care how it's moving though. And so for a very slow particle, the electric force is going to win. It's a very slow particle. Maybe very isn't the right word. But, yeah. Because we can consider, like, say we have a faster, or let's say we have just a fast particle. But it's moving less quickly than this one. It's like just a fast particle would be going here. Whereas slow particle, so it's not very slow, but it's moving. So this one's moving faster than this one. And so it's moving faster, so magnetic force, there'd be more of an upward force. So it's not going to be forced downwards as quickly. There's going to have more of a curvature. However, there's this particle where velocity is, say, just right. So if the velocity of a particle is just right, it's going to pass through without being deflected at all. And so this device I described is called a velocity selector. So imagine we have a beam of particles. We can put like a plate here with a little hole in it to create a beam, but they're still going to spread out a little bit. And what we want to do is, let's put the plate on the other side. Here, let's create a beam of particles this way. And then we can place a plate here that'll block off all these particles that hit it. And so you can see there's a very narrow range of velocities where it's basically just got to go straight through. So if there's a difference between the magnetic force and an electric force that deflects a particle, it's going to hit this barrier and stop. And so basically, if you have particles with different velocities over here, like one example of this would be, say you have an ionized gas and you just let it go. You say have a container, put a little hole in it, so particles are going to be shooting out of there. But again, we saw from just talking about gases, the velocity has a distribution. They don't all go the same speed. So we've got a variety of particles coming through here. Some are going to be going fast, will be deflected upwards and hit this barrier. Some are going to be going slower, they're going to hit this barrier. So we can pretty much fix and just say a particular velocity of particle is going to make it through this velocity selector. And what's required to make this is a constant electric field, which we can make with a capacitor. Also a constant magnetic field, and there is a way we can create a constant magnetic field, That's a device called a solenoid. And so, yeah, we could build a velocity selector with a capacitor and a solenoid, and you can pick what velocity is going to get through there. And again, the criteria to make it through is a net force of 0. So if there's no force in this y direction, there's going to be no deflection, it's going to go straight through. So if we set this equal to 0, we can see that E has to equal VB. We're assuming that the charge isn't 0. And so if we want to solve for the velocity that's going to get through, we get the simple result. This will allow a velocity, or the velocity given by the ratio of the electric field over the magnetic field. So let's do an example of that. I'm going to write down the result. Oh, I'm going to say one more thing about this. What if we replace a positive charge with a negative charge? Nothing really is going to be different here. It's just like flip this picture upside down. For a negative charge, remember the force on the negative charge is in the opposite direction of the electric field, the electric force. So the electric force would be up, but the magnetic force would be down. So they're still completely opposed to each other. So, yeah, I mean, here these would be very slow particles, these would be very fast particles, but basically the same thing. It's just the force would be in the opposite direction, but you get the exact same result. So let's build a velocity selector. Should point out that these particles, usually when we talk about these charged particles, like a beam of charged particles, they're moving very fast where air resistance could be significant. And so let's say we do this in a vacuum chamber just to make life easier. And let's say we want to have a velocity selector where we, let's say we want to allow particles to go through if they have a velocity of 650 meters per second, and that's it. And the electric field, well, let's say, I'm just making up a number here. Let's say 8 newtons per coulomb. And the question is, what magnetic field would we need? So in a sense, this is a very trivial calculation. B would just be E over V. And we know E and V. So I said, in a sense, it's a trivial calculation. But getting the units to work out, that's going to be the tough part. But let's do that. So we have B equals E over V, just by moving things around. Move B over here, V over there. Okay, so let's plug in the numbers. We have 8 newtons per coulomb. The velocity is 650 meters per second. So somehow this is supposed to give us Teslas. Okay, well, we have a new conversion factor. Let's use it. Actually, the units are not going to be as difficult as I thought they would be. Everything is just going to cancel out right away. Yeah, so let's look at the units. We have newtons times seconds, coulomb, meters, and Tesla. Coulomb, meters, newtons, and seconds. So yeah, we will get something in Teslas. And again, it'll be kind of a small value. Let's convert to milliteslas. So what we'd have 8,000 divided by 650, and let's do that. 8,000 divided by 650, so 12.3 milliteslas. And then we would have the, we know how to design our velocity selector. So if we did that, this particular velocity selector would only allow our particles moving with that particular speed to get through. Of course, maybe they could be going a tiny bit faster or a tiny bit slower, but roughly, they'll be moving the same speed. If they're too fast or too slow, they get deflected and blocked by that barrier. So, Now, I will say one more thing about a velocity selector. Now, it involves two things. We'd have a capacitor to create the electric field, like a parallel plate capacitor, and then be hooked up to a battery, so we can adjust the electric field just by changing the voltage. Now, we haven't talked about the solenoid yet that creates a magnetic field. We haven't really discussed that, but the solenoid, we'd have to drive a current through it, and the strength of the magnetic field would depend on the current. So we could change the velocity by either changing the voltage on the capacitor or the current in the solenoid. So we could have like a variable velocity selector where you could just adjust it very easily just by changing current or voltage. So a very practical device. And just, whatever is coming through is going to be moving the same speed. Okay, so I think that will be it for today. There's actually one more topic in the notes, but that'll take a little while, and I want to keep these videos, manageable pieces. So I'll stop this one here, but then I'm going to have another one. There's a device called a mass spectrometer that we're going to talk about. I'll do that in a separate video, though. So we're done with this one.